In this video, we will look at parametric equations. Parametric equations are in this section with the rest of the conics, not because they are a new type of conic section, but because the equations that we get from parametrics most often produce conics. So what are parametric equations? Well, parametric equations are a pair of equations, two equations that show movement. One equation shows the horizontal movement, one equation shows the vertical movement. They're called parametric, not because they're a pair, P-A-R-A, parametric. They are using a parameter, a third variable, to express that movement. So our horizontal movement is going to be an x equation, and then our vertical movement is going to be a y equation. So these two equations can show us the direction that an object is traveling over a given period. So our third variable is going to be t. That is the parameter that links the two equations together. So again, parametrics, two equations, one shows horizontal movement, that's an x equation, and one shows vertical movement, that's a y equation. I'm going to be doing some graphing of these. We'll do them all by hand, and then I've got both the 8384 as well as an Inspire to show what that looks like on the calculator and how to do that. I actually prefer the older calculators, 83s and 84s. They are a little bit slower, which is actually a good thing here because they show the movement of the curve a little bit better than the newer calculators. But we'll get that when we take a look at those. So here is one last piece of information that we have been dealing with rectangular coordinates, and that might not be anything you've ever heard of, but that is the coordinate system that we've been working in for the entirety of algebra and now this course, pre-calculus. So we use x and y in the same equation, and it plots onto our Cartesian xy grid. It's everything we've known and done. There are other systems that we can graph in. We're not going to, but those include things like polar coordinates. So there are other ways, these parametric equations as well, that we can graph things. So the first equation, we'll just get into the example here. What they're going to ask us to do is they're going to ask us to take this set of parametric equations and graph the curve. Now when we graph the curve, it should be a part or whole of a conic section. So when I say part or whole, for these first few, it'll be part of it, just a segment of it, and then later on we'll see whole conic sections come out. So what we need to do is go all the way back to the basics of graphing and make a chart for this so we can plot some ordered pairs. Now I didn't give myself a letter in there, but the biggest thing here is to realize where our time is. So they're going to give us that parameter, that time. When they're asking us to graph, they have to give us that to know for these where to graph that. So what we're going to do is we're going to pick numbers between, well, in this range, to plug into both of these equations. So instead of just an xy table, we're going to make an xyt table. There's a few different ways you can do this. Let's see, we'll do the t in the middle this time. So xyt table. Okay, so there is a little bit of benefit to thinking about numbers that you're going to plug in. You can't just plug in all of the whole numbers from -4 to 4 by all means, and that'll get you some answers. You don't need to, that's a little bit overkill. You really only need about 5 or 6 points to figure out the curve. And if we look at our equations, there are good numbers to pick that will give us whole numbers for our answers. So if we pick anything that's divisible by 2, that part in the y equation will stay a whole number. So not a bad idea to go through and kind of think about what numbers you should pick. You're never going to get wrong answers as long as you're doing good algebra, but it's a little bit harder to graph, like 3.5 versus 4. So just keep that in mind when you're picking your points, but at least 5 points to pick, and write those in for the t column. So I'm going to go with -4, -2, 0, 2, and 4. Okay, and now we plug those in. So we want to plug each of them into the x and y. You can do -4 and plug it into both and then get 2 answers, or you can go down the list for x, which is what I'm going to do, and then go back down the list for y. So if I plug in -4 to the x equation, that's going to be negative 4 quantity squared plus 5. That's 16 plus 5, so 21. Negative 2 is going to be 4 plus 5, so 9. We plug in 0, we get out 5. Then the positive 2 and positive 4, those should be the same as the negative since we squared it, so 9 and 21. Okay, there we go. We have our x's for this parametric curve. Now we're going to do the same process for the y, so we have negative 4 over 2, which is negative 2. Negative 2 plus 4 is positive 2. So this one's not going to be symmetric, but there is going to be a pattern to it. It is a linear equation, so we should see a little bit of a pattern here. Negative 2 over 2 is negative 1, plus 4 is 3. We plug in 0, we get 4, and you can hopefully figure out the pattern at this point, so 5 and 6. And that's why it's important to pick those whole numbers, because it shows us this pattern, and it's a little bit easier to do the rest of the math. Okay, so now we're going to go on to graphing this. And we're not going to magically fit a third axis into our xy coordinate grid here. We're going to plot x's and y's. So how's the t going to come into play? Well, the t is going to show us the movement of this graph, so the order in which we graphed it, which is kind of weird to think about. But it's going to show us the order in which we graphed it. Right? So let's take a look here at the calculator to see. This will turn on here. There we go. First thing we need to do is change the mode to be able to graph this. So I'm going to go into mode. And then if we look down here on the fourth line, it says PAR, which is parametric. So function is our normal mode. Parametric is what we're doing today. POL, that's polar. We're not getting into that. But we set that. Then we'll go to quit. And now when we go into the y equals, you'll see that's an x and a y, which is exactly what we had here. So the x was t squared, and you don't need to go hunting down here for the alpha t, which is here on 4. If you just press the x button, you'll see there's x, t, theta, and n. It now becomes a t. So the calculator is programmed, it knows what it's doing. I don't. Let's put a square up there. There we go. All right, so t squared plus 5. And then for the y, it was t over 2, so t over 2 plus 4. And then one last thing we need to do before we graph this is we're going to go into window, and it's going to give us some different options. So it's going to say tmin, tmax, tstep. Those are new. We've never seen those before. So the only two things that we're going to adjust is tmin and tmax. So tmin should be your lowest time value. So for us, it's negative 4. And then tmax should be your highest time value. For us, it's positive 4. T-step, that's just how often they're going to plot points. They're going to plot points once every 0.1308, 09, and that's going to just sort of determine how fine the graph is. You can mess with that and see what happens. The larger numbers you put in, the less accurate the graph is. The smaller, the more accurate. But the smaller numbers you put in, the longer it takes to graph. So bigger is less accurate but faster. Smaller numbers, more accurate but slower. Okay, so let's hit graph and see what it does here. Okay, so that was pretty quick. Hopefully you caught that movement. If not, you can pause this and go back. The graph started here and then came in and then went back out. All right, so that is what we're looking for with our T movement. Now that would be different if we were doing a different function. When we were graphing in rectangular, our functions always start in somewhere on the left side, do their movements, and then come out the right side. That's not the case for these, and we'll see some other ones later. But it started here, went that way, and came back up. Usually we can't graph functions like this because that's not a function as defined, the first chapter of the year that you do here. So this is not passing the vertical line test, but we're still able to graph it with this set of parametric curves. Okay, so I'm going to abbreviate my graphs here. We'll go by, oh gosh, I don't know. 2's is not going to be good. We'll go by 1's, I guess. that's 21. This will be a little bit bigger of a scale here. That's 7. So the first point we would plot is 21, 2. So 21, 2 would be right there. Then we go to 9, 3, which would be there. And then we'd go to 5, 4. Then we'd start back around the other way, so we'd have 9, 5, and 21, 6. So that is a sideways parabola. Now the last thing we need to do is connect these dots. And this is very specific to parametrics and very different than how we've done things. We don't just want to make a big line that extends forever through these and call it a day. This has endpoints, as denoted by those equals. So these dots are ends that does not go on forever, and they are filled in since it's equal to. We want to mimic the movement or the order that we plotted these dots. So we started here and we ended up here. So that's how we need to graph this. Now if you just look at it, you couldn't tell if I went one way or the other. So how do we indicate that I did make that movement, that sort of clockwise movement? Well, what we do is we add arrows onto the graph in between the points. So those arrows indicate the direction of movement. They indicate that we started at 21, 2, then went to 9, 3, and then 5, 4, so on and so forth. So that's how we indicate the parametric. So it's a lot of little details to get that graph. That's what it should look like, and we'll take a quick look here at the Inspire. If I can get it. There we go. So for the Inspire, it's a little bit different. If you go into the graph and you go into Menu, Graph Edit Entry is option 3, and then option 4 here is Parametric. So this does everything on one screen, which is nice, but you'll see why I don't quite like this here in a moment. So we do need to use the variable t-squared. That time you have to use the correct key. The equations are the same, so over 2 plus 4. Okay. And then down here, they actually put the t-step on the screen, so you don't forget to change that. So our t-max was 4, and our t-min was negative 4. So that's a little bit more user-friendly there, where you see the exact same that we had right here. And don't mess with the t-step, just leave it at 0.13. Good to go. Okay, and then I'm going to hit enter. It's going to happen very, very quickly, so much so that you can't actually see which way it's moving. Boom, it's just there. So that's why I don't like this one as much, because it does not show that movement. It just all shows up instantly. We can change this, zoom fit. We'll see what happens there. There we go. So there is the parametric curve, and it's looking exactly like what we had, but we don't see the movement on the screen. So for this calculator, you can go into Table, so Menu 7, Split Screen Table, and it will show you those same values that we had. I don't know why it goes on past. Oops. There we go. So 4 gave us 21 and 6. 3 gave us 14. We didn't do 3. 2 gave us 9 and 5. So there's the table, the same as we had right on the calculator for you there. And it goes on even though we didn't go to negative 5, so just be careful that it gives you extra values there. All right, back over to this one. If we go into second graph, it also gives us that same table, everything we need there. So if you prefer to do it this way, use the calculator to get the information for you, that's totally fine. Just make sure you put it into parametric mode and then get the numbers from the equations, or from the tables there. Okay, so this example is similar. If you would like to pause the video and give this one a shot, see what happens for this set of equations. Okay, hopefully you've taken a moment to work this one through, and if you did, you might have noticed something a little bit fishy. So let's take a look at this. So for this equation, we have x equals t squared plus 4, or sorry, t squared over 4 plus 5, y equals t over 4 plus 4 between negative 8 and 8. So again, I want to start with making an x, y, t table. I'm going to put t in the middle again. I like that. That worked out last time. So there we go. So we now have a bigger range of numbers, negative 8 to 8, and we have fractions in both of the t portions of the x and y equations. So what I would suggest doing is picking values in our time that are divisible by 4. And it just so works out that if we do that, we get 5 values again. So -8 is divisible by 4, -4, 0, 4, and 8. And 5 values is a really a good number. If you have fewer than that, you might not get the exact curve of it. You might miss a point of the curve, might not look symmetric. If you have more than 5, you're never going to be in bad shape doing more. It's just more work to do. So 5 is usually a pretty good number. Okay, so once again, I'm going to plug in numbers for x and then just do that whole column and then go to y. So if we plug in -8, -8 squared, that is 64. 64 divided by 4 is 16. 16 plus 5 is 21. -4 squared is 16. 16 divided by 4 is 4. 4 plus 5 is, wait a second. We plug in, that's 5. And this is symmetric, so that has to be 9. And wait a second. We just did that. We just got those same numbers. Curious. Okay, for y, if we take -8, -8 divided by 4 is -2. -2 plus 4 is 2. -4 divided by 4 is -1, but that's 3. That's 4. So that's 5. That's okay. We got the exact same values again. So we had different curves, t squared over 4 plus 5, and t over 4 plus 4. We had different time values, -8 to 8, but we got the exact same coordinates. So what does this mean? Well, what this means is that these two equations produce the same curve, they just produce it at different times. So what's happening here? If we would graph this by hand, we would still get 21, 2. I'm just guesstimating here. This should be pretty close. That's 5. I can see that. 6, 8, 9. So we still get the same curve. What's happening though is this second curve, since it was from -8 to 8, it took longer to make. So it took more time to generate that curve. Instead of it taking the 8 seconds from -4 to 4 that it took in the first example, this one now took 16 seconds to make that same curve. So if we go up here to the problem that we just did, I'm going to do t squared divided by 4 plus 5, and then t divided by 4 plus 4. And then I'm going to change in the window setting here, this from -8 to 8. Now what should happen is we should see this form a lot slower. I'm just going to go to zoom fit. And that's forming a lot slower. Still the same curve, the exact same shape, same direction of movement, it just formed a lot slower. So how would you indicate that if you were just doing this on paper and pencil? Well, there really is nothing to indicate on paper and pencil. They could ask you, compare the two graphs, what's the same, what's different. If you compare these two sets of parametrics, they are the same curves. They give you the same graph. They all have the same x and y coordinates that are linked together. 21 goes with 2, 9 goes with 3, so on and so forth. You would say that the second equation takes longer to generate, since it has a longer time span covering the same distance. That doesn't really have much context when we're just dealing with x's and y's. Where that more comes into play is when we apply these to physics. So this set of parametric curves has a very important physics application, and we'll get to that not in this section of notes, but as a continuation of this in the next video. So the t doesn't really do much for us right now. It just makes it take longer to form. The only way we can really indicate that is just having that t interval on our paper. Okay, so the last thing we're going to do is we're going to convert parametrics to rectangular. So converting parametrics to rectangular is pretty easy. It's basically just a substitution problem, And the hardest part will come in rearranging the first equation. After that, it's pretty straightforward. So what we want to do, if we're given a set of parametrics and they're asked to be written in rectangular, we want to solve the x equation for t. We always want to resolve the x and plug that into y. That way we have a y equation in terms of x. That's how rectangular equations are written, like y equals ax squared plus b, or y equals mx plus b, something where the y is all by itself and the x is on the other side. So that's what we're looking for here. So it's not a super involved process, especially on this one where there's a very simple x equation. When we have a little bit more advanced x equations, it can get a little bit troublesome, but for right now, they're pretty straightforward. So we're just going to bring this equation down here, x equals negative 3t, and we're just going to solve and get t by itself. So it's a one-step solution. We just divide both sides by negative 3, and we get x over negative 3 equals t. So the first step is to solve the t equation, resolve it for t, the x equation, excuse me, resolve the x equation for t, and then plug that into the y equation. So we had y equals t squared plus 2. Instead of that t, we're going to plug in this quantity. So y equals x over negative 3, don't know why I made that so big, squared plus 2. And you can leave it just like that. That's perfectly acceptable in terms of an answer. If you're looking for something specific, say on a multiple choice style test, they'll probably go ahead and square that out. So the numerator would be x squared. The bottom would be positive 9 plus 2. Okay, so I'm going to get both these calculators going at the same time here. I'm going to use parametrics on the Inspire since it's a little bit easier to do that one. I'm going to close this table first. And we should be able to delete everything, and then we'll put in a new parametric equation. So we will plug in the 3t, negative 3t, and then we have t squared plus 2. And we are going from, this always defaults to 0 to 2 pi. Oh, they didn't give us a t step here. So we'll just go with that because they didn't give us one here because we're not supposed to graph this. Just kind of showing you that these are the same equations. Good enough. So we'll go to zoom fit. And we have that. Okay, cool. So that is kind of the standard window there. I'm going to try to undo that. We'll see what happens. Nope. All right, so we'll have to go back from 0 to 2 pi. Making this a lot more complicated than it needs to be, I know. Oh, we're doing this one in rectangular coordinates anyway, so that doesn't matter. So I'm going to switch this one back to function, and then we're going to plug in that new equation we got, so x squared over 9 plus 2. Now, it won't look exactly the same, but it should have that same branch over there. So I'm going to go to zoom standard, and we see it still has that same starting branch that we had over here. If we made this t a little bit longer, then it would have that whole curve, but those are the same, and if we need further proof, we can go into a table, and we can see at 1, it was, oh, these would be related values. So the 0 for x is 2 for y. So 0 for x is 2 for y. So those numbers do match up right there. Okay, enough of that. It is correct. The work is pretty straightforward, so very low chance that we mess that one up. But that is the gist of the work that you want to do to convert it into rectangular. So there is another example right here. A little bit more challenging, but not crazy. They do give us a restriction on t only because we have a square root and a t in the denominator. So the denominator can't be 0, the denominator, the square root part can't be negative, so they give us a restriction that t is greater than 0. That's not really we're not graphing this, so it's not uh, like a parameter that we're going to be using in another way. It's just to keep everything as a real number. So the work again is to resolve this equation, get t by itself, and then plug that value into the y equation. So if you want to take a go at that, pause the video and do so now. Okay, so the first thing we're going to do, it does also say graph, I forgot about that part, but we're going to resolve this equation. So we have x equals 1 over square root of t. There's a couple different ways you can go through this. It's the same steps, it just doesn't really matter the order as long as you're doing all the same work. Instinctually, first thing might be to square it, and that's great. So we have x squared, and then we square that, it's 1 over t. There's a lot of different ways you can do this. Easy way is you can just swap the x and the t. That mathematically works. Here's the proof. Multiply both sides by t. So we have tx equals 1, and then divide both sides by x. So we have t equals 1 over x. Okay, so t is 1 over x. That's going to make a messy fraction on the other side, but we can handle it. So y equals, where there was a t, now I'm going to put 1 over x plus 1 over 1 over x. So now we have this weird complex fraction. So the easiest way to clean this up is just to multiply it by that denominator of x over x. So we get y equals, when we distribute this, that becomes a 1, that becomes an x, that becomes a 1. Okay, so we have that very simple equation, 1 plus x, and we can graph that. That's just a line at 1. The parametric, just to make sure we did it right, we'll go back into the parametric mode, and we'll do 1 divided by the square root of t, and quantity t plus 1 divided by t. And we have, that'll work. And I completely messed up when I was squaring both sides, solving the x equation. So apologies, that is the right work. I just did the wrong thing here. So we don't get a line. We do get that little piece of a curve. I forgot that this should be x squared because we squared both sides. That was the first step. So this is x squared the whole time. Apologies. So this is 1 over x squared, and that's 1 over x squared. So we're still going to multiply by x squared over x squared. Same process, just having a square there. So we get y equals, we still get the same thing, it's just squared. So 1 plus x squared. So it is not a line, it is a parabola. Okay, so how do we know that we are sort of on this part of the curve? How do we know that that's where we're looking at and we're not looking at the entire parabola? Well, that is partly from the t that they gave us to start. So t was greater than 0, which if we look, when we plug t greater than 0, we can never get a negative out of this, out of 1 over square root of t. We'll never get a negative number out of that. And if we do t's only positive, same thing will happen here. We'll only get positives out of the y equation. So when we graph this, what would be a parabola, we're only graphing the positive x's, which is only producing us positive y's. So we only get this right branch of the curve. It does go on forever since it's t greater than 0. And that's a very subtle thing dealing with domains of our original parametric equations. So if you don't quite get that part of it, not the biggest deal in the world. It's more important to be able to convert these into the rectangular. And again, we do that by solving the x equation for t, plugging that back into y. Just make sure you do it correctly. If you don't, you're going to get something that is not a conic, and that should have that's kind of what tipped me off, that we got a line, but then saw it on the graph, I put 2 and 2 together. the answers that we get should be parametric. So it should be, or sorry, conic sections. So it should be a parabola, a hyperbola, an ellipse, a circle. That's what we should get out of these. We should not be getting a linear equation. I think that'll do it for this set of notes. So the next examples we'll look at are some actual physics applications of this. But for today, all we need to focus on is plotting these, making x, y, t tables, getting our points. Very important to show the movement with the arrows on the graph, and then converting into rectangular. Again, we do that by solving the x equation for t, and then plugging that equation back into y. So that'll do it for these notes. Until next time.